Okay, YouTube, in this video we're going to be working on how to find nth roots of complex numbers. So in my last video we had looked at situations where we were taking these complex numbers that were maybe in standard form and raising them to the nth power. And we found that it was more convenient to do this if they're written in trig form, this RCIS theta form, where we know the distance and direction that our complex number is lying in. We said that if we were going to do this, we could use this nifty theorem called DeMoivre's theorem that says you just raise the modulus to the power, and you would just take the argument times this letter n right here. What I want to kind of build is this argument in this video that says if we're taking an nth root, that is, you have some number here that you raise to the power of n, you write it this way. When you're taking the nth root, recall that we can rewrite this as a rational exponent. This would be to the 1 over n power. And conceiving of it this way, we could say that this is no more than really RCIS theta to the 1 over nth power. So if this was like square root, we would have n as 2, we'd have to the 1/2 power. We're saying in general nth roots. So we'd say that by the consequence of DeMoivre's theorem, we'll just raise r to this power, this 1 over n power, and we will take our CIS expression here with the argument, and we will just take it times 1 over n. And this is essentially what we do when we find the roots of complex numbers in written in standard or trig form. We want to write them in trig so that we can use this property, but this is how you find their roots. And so I'm going to clean this up one more step here, and I'm going to say that really what we did was this. We took the nth root of r, and we took this times the CIS of theta, or cosine theta I sine theta, of 1 over n times theta, where I'm going to write theta as being over n. And the simple fact of the matter is this: because we want to, this is a periodic function here, we want to include all things coterminal with all of these, angles here. We would say add on the period of this function as well. And we're going to say that that is 2 pi times any integer here, but that must also have been split by n here. And the reason why, and I'll just show you the consequence really quickly here, is that we have really this. We said that it was 1 over n times everything in the denominator. We could look at this as the argument plus 2 pi k, plus anything coterminal with that angle would have happened. So we're going to say, and this is not a 2, this is an n, this is an n. But we would have had everything over n here. So basically, you get this 2 pi k over n. And what I'm going to do is I'm going to point out over here, because I've already got it written out over here. It says for a positive integer n, the complex number z equals r cosine theta plus I sine theta has exactly n roots. And not only does it have n distinct roots, it's given by this formula right here. So in other words, the square root of our complex number, you take the nth root of this complex number, the nth root, then it's just the power, or the modulus in front. We're going to take that to that power. We're going to take the nth root of that, and then we're going to say it's cosine of theta over n. So instead of multiplying by n, we're dividing by n. It's just we have this really weird plus 2 pi k thing that's going to sit in here also. And we'll do a couple of examples and talk about how it makes total sense. It does. But we say that k, just to let you all know, k is actually every integer starting at 0 up to n minus 1. And if you wanted to make yourself a note here, we say that it is 1 less than the indicated root n. So if you're taking a 5th root, you would say k is 0 through 4. If you were taking a 10th root, you'd say k is 0 through 9. So what we're going to do in this video is we're going to find a couple of roots here of complex numbers. We're going to start with this one right here. It says z equals 16 cosine I sine 60 degrees. So I am actually going to truncate this, write this in the shorter of the two forms, cosine I sine of 60 degrees, and I'm going to write exactly what it is that we want to find, which is the square root. I'm even going to put the 2 out here in the index. So since this is already in trig form, then using this theorem, we say that we will just take the square root of the number in front, and then we'll do CIS. Now here's the part that's not tricky. It's not tricky at all, but we're saying that n is 2 here. So we have 60 degrees plus 2 pi k all over 2. And we should split this up, as a matter of fact. And this is something that I would do going forward. And actually, by the way, the square root of the 16 here, we're going to say is 4. And we have CIS. Now, I'm going to split this up and say 60 over 2 is really 30 degrees. And 2 pi k over 2 is actually equal to just pi k. Sometimes you have a fraction here and sometimes you don't. But the idea is this. This right here is the set of all square roots. Okay? But here's the thing. There are infinitely many square roots, but only 2 of them that are what we say distinct. That is, that we can tell the difference between them. So what we're going to do here is we're actually going to say, well, then what are these two roots? Recall that k is going to assume all values starting at 0 and going up to 1 less than n, and in this case our n was 2. It is 2. So we're going to say, well, I'm going to plug in 0 for k and I'm going to plug in 1 for k. And what you get are two distinct roots, the first one being 4 CIS, and then we have 30 plus. Now if I plug in 0 for k, this cancels out completely. So we're going to get 30 degrees for our argument. I did not mean for that to be a different color. I apologize for that. And we say, all right, plug it in a 1. If you plug in a 1 here, this pi, I guess, if we were to convert that to degrees, it would be like a 180. So we have a 180 plus 30 degrees is 210. So funny thing about complex roots, if you were to graph them, so that is, we have a number here that's going, in a 30-degree direction. I say this is maybe a 30-degree direction here, and this is a distance of 4 because I said so. If I were to go to 210-degree direction, it's actually down here. We say going out a distance of 4 here, we say r equals 4, and I've got a 210-degree direction. You see these complex numbers actually sit on the perimeter of a circle if you wanted to be analytical about it here, and they are evenly spread apart this circle. But for now, we just need to know those are the two complex roots of this. And these are easy to convert back into standard form using methods we've already explored. So let's go ahead and take a look at this one here. It says find all 6 roots of 1, which means I've got to get 6 different answers for this thing. The key here lies in the fact that this 1 right here can be interpreted as being 1 plus 0i. Which means we can actually go write this in trig form. As a matter of fact, I don't even have to go through my normal processes to find this in trig form. I just need to know how far away it is from the origin and what direction it's heading in. And 1, 0, you guys, is sitting right here. So as far as its direction angle and its distance, I can say right out, beyond a doubt, r is 1. We say 1 cosine I sine, and its direction angle here is 0 degrees. So if we're going to find all 6 roots of z, then we need to find all 6 roots of 1 cosine I sine 0 degrees, which will mean for us essentially this. We have n equal to 6, theta equal to 0 degrees. We are going to get the 6th root of 1 cosine I sine of, now 0 degrees is our theta, plus 2 pi k, all over here, n, which is 6. So, just using what we have over here, the only thing that we have responsible for, left to do is evaluate this root in the front, which, by the way, comes out to be, you guessed it, 1. Also, this. We have to kind of split this up and say, well, 0 divided by 6, 1 CIS, 0 divided by 6 is 0 degrees, plus 2 pi k over 6, which, by the way, the 2 and the 6 cross reduce. We get 1 and 3. So I get pi thirds k, which pi thirds is really a 60 degrees angle, 60-degree angle. So we say, well, what is k going to equal? Since we were finding the 6th root, k has to equal everything from 0 up to 1 less than that n value, which is 5. So if you plug these all in, we get 6 roots. I'm going to write them all down here. I get 1 CIS 0 degrees. How did I get this? I plugged in 0 for k and this dropped out completely. So the first root you always get. You notice I got the same thing over here. It was 30 right here. You're always going to get 30 as your first root in that case. 0 is your first root in this case. Whatever this number is right here, that's going to be in your first root's argument. So now writing the rest of these out, I get CIS. Now here's the kicker. This is a 60 degrees, and I should get that slash out of there. Okay, there we go. Now I can fix this. This is now 0 plus 60 degrees times k, where now k's gone up by 1. So now this becomes 0 plus 60 degrees times 1, or in other words, 0 plus 60 degrees. So this is CIS 60. I have 1 CIS now. If I had 0 plus 60 degrees times 2, that'd be 120. You notice that this went up by 60 degrees each time. And this is going to keep happening. As a matter of fact, we're going to do this as long as we are staying with angles between 0 and 360. So add another 60 on top of that. And you notice here that if we were to add 5 times 60 to this 0, we would get 300. The reason why we stop at, instead of going up to k equals 6, is because if n is 6 and our k is 6 here, those would cancel out completely in this expression here. If n was 6 here and this was 6, say, these would cancel out completely and you just say plus 2 pi, which lands you back at the exact same angle. So these are six complex 6 roots of this number 1. I bet you didn't know that it had 6, but these are all 6 of them. Cheers.